we'll look at the different types of operators, basically define them, and really this is a carryover pretty much from the case of matrices as well. They have different types of matrices, and here it carries over to quantum mechanical operators. The inverse operator, suppose M is a quantum mechanical operator, it's linear, and then its inverse is represented by M inverse, and that's a matrix or a operator such that M inverse is equal to M inverse M, and when I multiply either of these fashions, I get the identity operator. So like matrices. Here, of course, the identity operator is like an identity matrix. When I operate on any state, then I just get the state back again. I can operate on it from the left or from the right. Notice on this, never write operator A over operator B. It's just bad notation. It's ambiguous. So rather, depending on what you mean, either write A operator B inverse or B inverse A, because in general, remember, operators do not commute, so refrain from writing them as ratios or fractions. There are some properties that are true of matrices. They're also true of quantum mechanical operators. If I have a product of operator A and B and take the inverse, well, that's the equal to B inverse A inverse, in which the order is switched. So you do it in reverse order. Sort of a similar one, you can take for n an integer, an operator to the integer n power and take its inverse, and that is simply the inverse of a to the nth power. We define the Hermitian adjoint, or sometimes called the Hermitian conjugate, and it's really a series of things depending on whether you've got a scalar, a vector, or a matrix operator. Okay? For a scalar, little a, then the Hermitian conjugate or the Hermitian adjoint of a scalar is just the complex conjugate of it. For Bra vectors, sorry, for a ket vector, uh, the Hermitian adjoint or the Hermitian conjugate is just the corresponding Bra vector, and vice versa. For this Bra vector here, the Hermitian adjoint is just this corresponding ket vector. For operators, is a little more complicated definition. Really, either it's defined in one of two ways if you look at them, either this way or that way. The way I like is sort of this one, in which I can move this operator operating on A, is the way I would look at it, over to here by simply coming in and doing the adjoint operator on phi and then bracketing it with psi. So that's the way I usually define the adjoint operator A dagger. Lots of books, and you can show these two are equivalent, but again, if I bracket A between these two, I can think of A as operating on this state, and it's going to be equal to, if you look at this, the adjoint operator, complex conjugate, but now the order is reversed. I'll have phi and psi. Here I've got phi and psi this way. This one's psi and phi, they've been switched. And if I take the adjoint operators, the operator that's defined in such a way that if I operate on with the adjoint operator on phi, and then bracket it with psi and complex conjugate, I'll get the same as if I'd done it in this order over here. So those are equivalent. There's a whole slew of properties. I'm not going to go through those to any great degree. When we need them, then I'll talk about them. One that's kind of interesting is this combination here. We haven't really talked about that yet. This is actually called an outer product of these two Bra and Ket vectors. And but as you might imagine, with these, can take the Hermitian adjoint of that, and you just switch the order of the two, and then also make them their adjoint operators. As a practical matter for matrices, remember the Hermitian adjoint is I simply interchange rows and columns and take complex conjugate of everything. And you can check, but if I have this and this, then these two operations with this particular matrix for A will give me the same result on either side. I won't supply the details, but you can do that calculation. Hermitian operators we've already had before. A operator is Hermitian. I represent it here as H for Hermitian. If it's its own adjoint, so the Hermitian adjoint of H is equal to H back again. It's anti-Hermitian. Here I use capital A for anti. If I take the adjoint of it and I don't get A back again, that would make it Hermitian, but I get minus A, so it's sort of anti-Hermitian. Sometimes you'll hear people talk about that. Unitary operators, it turns out for unitary operators, the Hermitian adjoint is equal to the inverse. Or another way to say it is U times its Hermitian adjoint has to be the identity operator. Kind of an interesting theorem that has some application. If U and V are both unitary, then so is their product. Projection operators, we'll see more about those subsequently. But a projection operator is a Hermitian operator. If you look at this just says it's Hermitian if P adjoint is equal to P, but also we have that P operating on itself, or P squared, just gives me P back again. And there's some interesting results that I'm not sure we'll use them in this class, but you may at some point encounter these. But if P1 and P2 commute, i.e., I can do any order, and they're both projection operators. So two projection operators, P1 and P2, and they commute, then either P1, P2 and P2, P1 are also projection operators. In other words, they have this property up here. Not a hard theorem to prove, but certainly again, some terminology. An orthogonal projection operator is one or two projection operators that when I give their product, I get the zero operator. So those are called orthogonal for pretty obvious reasons. And then a theorem that is sometimes useful in decomposing the quantum states, quantum space, is if I've got the sum of these projection operators, maybe n of them, but if that sum is a projection operator if and only if pj, pi, pj for any I and j up here is 0. In other words, if all of these projection operators are mutually orthogonal, then this sum of them is a projection operator as